Hi everyone, and welcome to our Wednesday seminar. Today is a double pleasure. Well, first of all, because we have an excellent speaker and a very good friend and colleague of mine. So Dr. Cruces from the Max Planck Institute for Radio Astronomy in Bonn. So first I will say a few things about Mary. So Mary is a postdoc in Bonn at the Max Planck Institute, and she works at with the fundamental physics group. And she is an expert on time domain surveys for pulsars and fast radio bursts. And she has many contributions in these two fields. And she has also worked and led extensive collaborations with, with Chinese colleagues from the Chinese Academy of Science, and she has used the new FAST telescope to study and discover fast radio bursts. So Mary did her studies in Chile at the University of Conception. Did I pronounce that right, Mary?
Concepcion, yeah.
Concepcion, oh, sorry. And then she also has an MSc from the Pontificia Universidad Catalunya de Chile. And she obtained her PhD from the University of Bonn, where we met, and she graduated in 2021, and she continues there as a postdoctoral researcher. So, and the reason I'm doubly, for my double pleasure today is because she's also going to give the first formal introduction of ARGOS, which is the new telescope that we're trying to design here in Crete. So Mary, thanks again for accepting our invitation, and the floor is yours.
Well, thanks you very much for the invitation and for the introduction. So today I will be discussing with you bright radio flashes at extragalactic distances known as fast radio bursts, and what is the context or the potential of ARGOS within this research field. So what you can expect in today's talk is first to go through the basis of what we know about FRBs, what we have learned through the several observations we had for the last 15 years. So to remind you that this is a relatively new research field, and then what are the open questions, and in particularly what we would want to know. Naturally, here I'm biased towards what I think is the most interesting part, and because of the duration of this presentation, I cannot go through all the things we have learned from FRBs. So there is a bias there, but with the disclaimer out of the way, to the last part, we will move to trying to understand what's the role of a potential radio facility such as ARGOS to be held in Crete. So let's start. It all began with pulsars and pulsar surveys. Back in 2007, there was a reprocessing, an extensive reprocessing of Park's archival data, upon which a bright flash of millisecond duration was discovered in the data. Because of the dispersion measure, it was immediately suggested that these sources came from an extragalactic distances. And when I mean with the dispersion measure, what I mean is, you can take a look at the equation that you see here, is a parameter that is a proxy for the free electron content along the line of sight. So for higher values, we would expect more content, or as well further distances. So for pulsars or any transient signal in radio, this parameter will be seen as a delay in the arrival times of the signal at the different frequencies. If we take, for instance, the Lorimer burst, which was the first ever detected fast radio burst, we see that the signal arrives first at the higher part of the band, and then there is this quadratic delay towards the later part of the band. So depending on the value of the DM or dispersion measure is how strong this delay will be produced. When we correct by the effect of the dispersion measure is where we have this integrated pulse profile that we see here. If we were not to do so, then in many cases, we will not see the source at all. So an FRB, a burst, was detected in archival data, and first it was thought it must be something extragalactic because this dispersion measure value was large. And contrary to pulsars, where if you take this value and then you correct, you will end up with values that will be consistent within the Milky Way. This is the case for the broad population of pulsars. However, for FRBs, if you consider the contribution along the line of sight, there was an extra term. And this is the equation that is shown here with the yellow box. So for the observed DM value of this FRB, we will have a contribution of the Milky Way that we can map with the galactic electron density model, plus a contribution of the intergalactic medium, which corresponds all the medium between the host and us, and the contribution of the host, and which is this small galaxy that we see here in the image. So this contribution of the host encapsulates the galaxy itself, but also the local vicinity of a fast radio burst. So when these bursts were discovered soon after, with the reprocessing and the ongoing surveys, more FRBs were discovered, but they all seem to be one-off events, which made the most popular scenario to be cataclysmic events. For instance, the collision of compact objects, white dwarfs, black holes, neutron star, or combinations of them. However, this changed when we discovered FRB 121102, which is the first repeating FRB ever detected. This was not immediate from the detection. This was an FRB detected by Arecibo, but with the monitoring, the continuation of the monitoring with Arecibo, it was discovered at some point that this source repeat. The importance of the repetition is that we cannot anymore say, okay, it must be a cataclysmic event that will lead to a one-off event, but instead there should be something that could produce a repetition. Or we have some events that repeat and some events that do not, which will stem for different progenitor scenarios. But most importantly, because now we have sources that could repeat, it means that we collect a sample of bursts and try to study them to understand what FRBs are. Because, as I stated earlier, they are an observational phenomenon, meaning that we observe, we detect, we try to understand them and constrain what could and what could not be the origin of this. So eventually, through the monitoring of FRB 121102, with VLA, there were some bursts detected, which allowed to narrow down the position of the source. Because usually when you have a telescope, the uncertainty in the position will be within your beam size, which could be several of arc minutes. However, through interferometry with VLA, it was possible to establish the location of the source to the small square box that you can see here. Multi-wavelength monitoring as well allowed to identify the host galaxy of this FRB, which was also an important proof to have the final proof saying they have an extragalactic origin. So what it was learned from FRB 121102 and this multi-wavelength monitoring is that it's hosted by a galaxy, a dwarf galaxy at a redshift of roughly 0.2, with relatively high star formation rate for its type. And from the observation that allowed to narrow down the position to sub-arc second, it was also seen inside of the box a persistent radio source, which was compact. We will come back to this topic because there is a full discussion of what could be the origin of this persistent radio source. What I would like you to keep in mind is that at the early stage, because as I mentioned earlier, we know this just from the last 15 years or so, until recently, we had more theories of what FRBs could be than the numbers of FRBs that we knew. We only knew tens of them, and there were hundreds of theories in the archive of how we could produce them. The galactic ones could early on be rejected because, as I mentioned, the localization of these FRBs and also the dispersion value as well. And then we were left with tons of progenitor scenarios in the extragalactic case. Some of them will account for cataclysmic events, so collisions of black holes and similar, or evaporating black holes, for instance. Some of them will be something like a supernova explosion that somehow will lead to these radio bursts as well. But in this scenario, we would expect some counterparts at higher energies and optical as well, which as of now, we have not really detected. So the observations of radio bursts are as of now restricted in the radio range, in particularly in the centimeter range, so somewhere from hundreds of megahertz up to 8 gigahertz. Because of the way that were discovered and many patterns like polarization properties or emission regions, then one of the natural explanations for magnetars were, for FRBs, were a population of neutron stars called magnetars, which is a neutron star with high magnetic fields, strong magnetic fields of 10 to the 15 Gauss. However, how magnetars could produce such a large burst detected at the distance of an FRB is not clearly seen. So for instance, to give you an impression on how bright these bursts are, is one burst with a millisecond duration could be as bright as the energy that the sun emits throughout the full day. So this is a quite impressive value. Some other of the progenitor scenarios, instead of go to larger scales, so instead of magnetars or stellar size sources, could be something like an AGN, a low luminosity AGN, that also somehow is producing these bursts. So, yeah, until recently, we had more theories than FRBs, but all this changed when FAST became available. So CHIME, this Canadian facility, stands for relatively low sensitivity, but large field of view, which allow us to have a full sample of FRBs and try to study their populations and some patterns. As of now, most of the FRBs that we know, which are above 1,000, were discovered by CHIME. What we have learned from them is that they are distributed all over the sky, that some of them repeats, some of them do not, and only a small fraction of them, less than 5%, actually repeats. And from the ones that repeat, an even smaller fraction of them are active. Many of them are seen only twice, and that's it. This brings one of the main questions in the fields, which is, do all FRBs repeat? We could think that maybe for the ones that haven't repeat, is because we haven't observed them for long enough. But at the same time, you have telescopes with chimes that can give coverage for some sources every day, and we have not seen them more than once. So it could be that, in fact, we have two populations of fast radio bursts, one in which we generate the repeating sources, and another one in which we generate the one-off events. While CHIME allows us to study the populations of FRBs, telescopes such as FAST, which is the largest single-dish radio telescope located in China, is a 500-meter in diameter telescope, and because of its sensitivity, it allows us to prove further distances or higher redshifts, so to find the most exotic objects. At the end of the day, the combination of the capability of each of the telescopes that we have is what allows us to find patterns in the bursts and try to understand more and more what are the most likely scenarios to explain fast radio bursts. So we have learned quite a lot. For instance, one of the things that we have learned is that the standard disclaimer that FRBs are bright flashes, radio flashes of millisecond durations might not quite be true. For instance, if we go to the duration, which up to recently was only 1, 2, or 3 milliseconds, somewhere in that order, we started learning that the parameter space could actually be quite broader. In one study that we did using Effelsberg as a main instrument, in which we collected 4 years of data and a sample of roughly 50 bursts, which meant roughly 160 hours, we detected many bursts, and one of them in particular, which is the one, if you follow the pointer, B31, which is one burst with a duration of roughly 40 milliseconds, which is the signal that you can see here. So this is significantly larger than the values that we are used to for FRBs. Furthermore, this tells us, by the way, that whatever parameter space we are using to search for this burst, we should expand it. Before this burst became available, most of the surveys will go to search something between fraction of a millisecond or 1 millisecond up to 20 milliseconds. The discovery of bursts like this wide, tell us, okay, the parameter space should be expanded. Furthermore, recent news showed that actually FRBs can be as narrow as a fraction as narrow as microsecond, which is the burst that you see to the right. This burst was discovered with the reprocessing of Arecibo data and is still work in progress. This work is led by Amsterdam group. So all these tell us, okay, the standard fast radio burst that we know might be in reality slow fast radio bursts if we have a burst of microsecond duration. And it also brings the question, are the second duration fast radio bursts, so ultra slow fast radio bursts? That could be. Another thing we wanted to understand is, we know that some of them repeat. Is there any pattern in the repetition? Is there any periodicity in particular that could allow us to associate them with neutron stars or with some binary or something along those lines? Well, the first discovery of a periodic activity window came with FRB 180916, which is an FRB discovered by CHIME. And for this one, because of the cadence that CHIME has over the source, it was possible to discover a 16.35 days periodic active window. If you take a look to the plot to the right, to the uppermost one, you can see here in gray as the band where the active phase is, and in white where the source is quiet. With the red triangles is marked where there were indeed detections. So one window, 16-day window, will be a combination of this gray band plus the white band. So roughly 40 to 50% of activity, and then a quiescence phase of the remaining days. And in this case, this is something that repeats. This is extremely interesting and was one of the latest milestones in the field, because it tells us that could be binary, could be maybe precision. And this was not the only FRB for which we have detected this, but also for 121102, which came soon after. The first study was by the group of Rushbait using Lovell data and all the available archival data. So in this case, they also put all the data together, combined it, and searched for a periodicity. What it was found was a 157-day periodicity in the activity and a 54 active phase. So again, here one 157 days will be the combination of the orange band plus the white band. Because we had with Effelsberg a large sample as well, which is the same one used where we found this broad burst, we used it to test the periodicity hypothesis as well. One of the reasons is because we were somehow concerned that when the archival data or the data that we publish is highly biased towards detections, because we tend to not show our results when we don't detect anything. And also because in the archival data, there was a mix of different frequencies from the megahertz up to C-band, so 8 gigahertz, 6 gigahertz, which we thought could be dangerous because maybe this activity phase or active window is actually frequency dependent. So we did a study with Effelsberg, and what we found was a 161 days periodicity. For this, we used only the data with our telescope at 1.36 gigahertz, so L-band. And the interesting fact is that we had full domain over detections and non-detections. And because our observation ran with no trigger, we were blindly observing. So the peak in the periodogram is the one that you see here that, in fact, is actually lower than 3 sigma. But if we go into in-depth analysis on the probability of a peak exceeding a certain value, then, and the study of the window, for instance, did I observe with a certain cadence without noticing every 2 weeks or something like that, this will be seen as peak as well in the periodogram. So we did these studies and we were able to reject certain peaks. And by studying the probability that this particular frequency will by chance exceed the threshold, then we realized that the signal was 4 sigma, which could be the case, for instance, in the presence of some red noise. If we go to the plot below the periodogram, we can see all the observations that we collected. And for this, in the yellow area, you can see the active window. So here, what you see in the x-axis is the phase, In the y-axis is the observation length. In magenta, you can see all the observations for which we had detections, and with the stars is marked where within those observations we had a detection. So one important or highlight here that I would like you to keep in mind is that even if you have observations within the activity phase, it doesn't mean you will for sure detect a burst, but instead, it means that you are more likely to detect bursts because we don't detect outside of the window. In order to constrain what's the duration of this window and to create a model to predict further activity cycles, we use the archival data, but only at L-band frequency, and then this is how we end up restricting the range. And this was regarding the periodicity. So, okay, now there is some hint, it could be maybe binary, it could be some precession there, but what about within the window? How much time do I need to wait until I detect a burst? So in other words, what is the waiting time between consecutive bursts? If I detect one event, what's the probability that another one will come after? So we did this because back then, before FAST was fully operational, we had this large data sample of 160 hours with Effelsberg, 50 plus bursts. So we were very happy with our huge, and I quote, huge sample. So we went to study, okay, is there a clustering in the events? Because it was proposed earlier that the waiting time between consecutive bursts was not Poissonian, but was instead a Weibull distribution with a K factor or shape factor smaller than 1, meaning that there was some clustering. This means that if you detect once, soon after another one will come. A Weibull distribution could be seen as a generalization of a Poissonian distribution, in which if the shape factor, which is this K value that you see in the y-axis for the plot, is equal to 1, we recover the Poissonian case. If it is below 1, it means that we have a clustering of events. If it is above 1, it means that there is some periodicity. So we did this with our sample, and what we found is like there is a clustering, which was interesting because we thought, okay, if we now know the periodicity of the source, maybe whatever clustering was there, it was just because we didn't know the periodicity before. However, some of you might have noticed that next to this white burst, I also plotted another one that is burst 20 and burst 21 in Cruces et al. Paper. And in here, what you see is two bursts, first B20, which is the brightest one, followed 40 milliseconds after by B21, which is dimmer. The importance of this burst is that it's telling us that bursts can come in package, so in short differences as short as tens of milliseconds. One natural question is, well, what if instead, because of the sensitivity of my telescope, this is the two peaks of a more complex burst in which I'm not distinguishing the intermediate component? So that could be the case. So then we will be biased in our analysis of the waiting time because I cannot differentiate if one burst is indeed one burst or actually the multiple components of another one, of a broader burst. So in this study, we rejected the bursts that were separated by tens of milliseconds, and this is how we come to the plot to the right. And in this case, if we subtract those bursts, then we find a K value that within 1 sigma is consistent with K equal to 1 or with a Poissonian distribution. This was quite cool, and we wanted to keep testing this. So we went to the Arecibo archival data, and we did again the same. If we took all the bursts, there was some clustering factor, but if we remove the ones that are shortly spaced, then it's perfectly consistent with Poisson. So what we suggested from this study is, okay, there could be two distributions for the waiting time. One that is the one that accounts for the tens of milliseconds separation that could be intrinsic to the emission mechanism close to the source, for instance, some magnetosphere. And there could be something in the tens of seconds, which could be showing another mechanism after the observations that we did with Effelsberg, fast, the Chinese telescope became available and did an observation on FRB 121102, or did several observations, and they detected 1,600 bursts or more. So this is, as of now, stands as of now as the largest sample. What they found is what you can see in the plot in the middle, which is by two distributions. So one, which is the one to the left, and accounts for all the bursts with durations of tens of milliseconds, or that are spaced by tens of milliseconds, and the other normal distribution. Afterwards, with Arecibo data, the same was seen, so you can still again see these two peaks. So this means, in principle, the broader distribution of bursts is consistent with Poisson. You could also argue look normal, but there seem to be two mechanisms at work. Something similar was as well hinted by the energy distribution, which means to count the number of bursts above a given energy value. So you will have the rate and the energy will be a power law. It's interesting to obtain this value for the power law or the slope because we can compare with some other sources. For instance, for the giant pulsars of the Crab pulsar, we have a gamma value of -2. For high energy bursts of magnetars, there is a gamma value of -0.7. Before our study, there were many different telescopes reporting different values for the gamma. So it was -0.7 that gave some hints that it could be magnetar. There were also -1.5. So we thought, okay, we have a larger sample, so perhaps we can see what's going on here. We did this, and that's the plot that you can see here. We took all of our data, so it's above 50 bursts. We excluded some ranges in which there were some instrumental effects. So to the right, or to the right side of the blue dashed line, it's rejected because it's the saturation limit. And to the left of the dashed red line, we rejected because it's the point of the completeness limits, which means we are not sensitive enough, so we start missing some bursts. So we did this, we found a gamma value of -1.1. And this was again different than what the other telescopes have obtained and for which there was no agreement. We propose that maybe the reason why different telescopes, which stand as different sensitivities, were obtaining these different values is because each of them were proving just a different energy range, which when FAST came with this sample of 1,600 bursts, nicely proved, as you can see here. So FARS allow us to go 3 times lower in sensitivity when you compare to what was seen before by Arecibo. And by this, it gave us the information that the distribution, the energy distribution was in fact bimodal. In this case, a composition of a Cauchy function and a log normal distribution. So the bursts with lower energy are distributed log normal. Again, this tells us that there are 2 mechanisms at work. So something producing the high energy bursts, which by the way is also changing in time. So in some activity phases, there will be a higher component of the energy bursts, high energy bursts, and in some other ones, most of the bursts will be lower energy. So this was in fact quite interesting, and it was another milestone in the understanding of FRB, and most important, explain, okay, why different telescopes were detecting different gamma values, because they were proving these different ranges. And that is for the energy, but coming back to FRB 121102, what I had mentioned early on, because it was the first repeating FRB, it stands as the most observed FRB and one of the favorite suspects. So whenever you want to test something, you go to this source because it's also quite active. So many of the things regarding fast radio bursts that we have learned is because we have this repeater, FRB 121102. So I said that when this source was localized, then it was discovered the persistent radio source, which is compact down to scales of micro arc second. This means that it's unlikely that this emission is coming from star formation, but instead it could be something like a low luminosity AGN, some nebula, or some supernova remnant, or something among those lines. But for a long time, we were discovering more and more FRBs, but there was nothing like FRB 121102, which made us wonder, okay, were we super lucky to find FRB 121102, and these type of objects are not common at all, because we were already at the point of having thousands of FRBs, 1,000 FRBs, and still nothing like 121102. Well, this changed with fast again with the discovery of FRB 190520, which already, upon discovery, it was evident that it was a repeating source because many bursts came within this 20-second observation. And I like to highlight here that FAST normally in their drift scan mode, they only do observations of 20 seconds, considering their beam size and the frequencies at which they are observing. So we extended the monitoring of FRB 190520, not just with FAST, but with GMRT, GBT, PARCS, Effelsberg as well, trying to find more bursts. And we were able to localize the source again with VLA. And with the same data, it was discovered that the source had a persistent radio source in the same spirit as FRB 121102. Furthermore, the host galaxy is also a dwarf galaxy with high star formation, and in this case also at high redshift. Though this is cool because we could say somehow that FRB 190520 is like a cousin or a twin to FRB 121102, but in many aspects is also different and has pushed even further our understanding of fast radio bursts. For instance, many of the information it came from FRB 190520 was from the studying of the dispersion measure. So this parameter that I showed you discussed earlier, and the rotation measure, which is a proxy for the magnetic field strength along the line of sight. Regarding dispersion measure first, if we consider all the fast radio bursts that have robust associations to their host galaxies, and then we can have the plot that is shown here. The repeaters are shown with the red field squares, while the non-repeaters are shown with the non-field squares. So what you see here is the model for the contribution of the intergalactic medium. So this means, going back to the equation we discussed early on, if I observe a source, I know the observed DM, then I model the contribution of the Milky Way, which is fairly understood. It can be up to 200 parsec per centimeter cube. Then whatever is left will be attributed to the intergalactic medium plus the host galaxy of the FRB. So the intergalactic medium model is the orange line, that you see here, plus the band which represents the uncertainty. So you see that most of the FRBs lies well within the model for the intergalactic medium, but deviations from this means that there is a larger contribution from the host galaxy. And the host galaxy, I emphasize, can be the galaxy itself or the vicinity, the local vicinity of the FRB. So for this case, for FRB 121102, there was already some indication that there was some excess, DM excess, hinting towards a dense environment around the FRB. But with FRB 190520, what we see is that the DM excess is way larger than for the other FRBs, so roughly an order, and around 3 times larger than for FRB 121102. This means that there is a high contribution from the host galaxy or the local environment. To understand this, let's think it in the other way. So let's imagine for this FRB, we don't know the host galaxy, so we don't know the redshift value. So then, okay, I know the DM because of the observations. Let's assume that the Milky Way along the line of sight will give a contribution of 113 parsecs per centimeter cube. The host galaxy is a dwarf galaxy, then the contribution could be something like 50 units. So then it means that the difference between the observed and subtracting the Milky Way contribution and the host galaxy will be something like 1,000 units. If I were to go to the plot and I go somewhere closer to 1,000, this means that the redshift expected for this, if you follow the pointer, will even be out of axis. We will conclude wrongly, and I like to emphasize wrongly, that the redshift value will be 2.2. And this is not the case, because we know the host galaxy from H alpha, we know what's the redshift value, then whatever excess is left must be associated to the host galaxy. In particular, the most interesting scenario will be to the local vicinity. So these FRBs are immersed in an extremely dense environment. But not only that, also, if we analyze the rotation measure, we also see that this local environment seems to be highly magnetic, not only dense. This was first shown for FRB 121102, which is the plot if you consider the full picture to the left. So the top panel, the blue dots correspond to the measurements for FRB 121102, the original repeater. And we see that throughout time, so 2+ years, we see that the rotation measure is decreasing significantly from 150,000 to 100,000. This is a large, it's roughly 30% change in the rotation measure. If you compare this with some other sources like the galactic center magnetar, which is the one plotted with the yellow dots, then you see that it's not changing as much. Here you don't see that it's changing a lot, but it's because of the scale. But if you were to zoom in, you will see some variability as well, but not even close as the values that we see for the original repeater. For FRB 190520, on the other hand, although the rotation measure value is not as high as the galactic center magnetar or the repeater 121102, we see that it's changing. And in this case, it's changing also in sign. So we go something from -7,000 to +4,000 units to -24,000. This data was taken with a GBT, but the similar is seen when we combine GBT and Parkes data. So we see a huge range there. It is interesting that this change in the rotation measure indicates a magnetic field reversal that for any other astrophysical source that is not Earth has not been seen before. And this rotation measure change cannot be explained alone by the change in the dispersion measure, which is also changing. So what this is telling us is that for at least FRB 190520 and the original repeater, there is a dense environment, highly magnetic, but also highly dynamic in the surrounding of the source. So we have learned quite a lot. So as a summary of this part of the talk, I would like to emphasize that nowadays we know many more FRBs. Most of them came in the last 2 years, so up to now we know roughly 1,000. But from this large sample, less than 5% of them repeat, and this is important. And from the ones that repeat, only a few of them have repeated more than twice. The most active sources are FRB 121102 and also FRB 190520. The duration of FRBs can go from microseconds to milliseconds and perhaps even longer. And from the energy distribution and the waiting time, we have learned that there could be two mechanisms at work, or that could be different highs in the generation of these bursts. And we also seem to know now that there are some particular FRBs, the ones that we have discussed the last, so 121102 and 190520, that have this association with a persistent radio source that we don't know what it is, but it could be key in understanding the origin of FRBs. And also for both of these sources, the host is a dwarf galaxy with high star formation rate, which could hint maybe, okay, magnetars. So So how do we constrain the progenitor scenario from here on, gathering all this information that we have just discussed? Well, we, in principle, could test two of the scenarios, which are the most popular ones, I will say, nowadays, in spite of the information we got in the last 2 years, for which FAST has significantly contributed to this. So we could have this scenario where we have an FRB with a magnetic companion, and this magnetic companion could be some stellar source, or it could also be a black hole, a massive black hole, or intermediate mass black hole. So in this binary case, well, the change in the magnetic field sign could be due to the orbit, and the persistent radio source, for instance, could be because of the black hole. If it is a low luminosity AGM, then the persistent radio source could come from there, or if it is a magnetar, somehow it could also come from there. But in this scenario, in this binary scenario, we would expect the dispersion measure and the rotation measure to be periodic. This means that we need to keep observing, because for these binaries, you could have something from some days up to several years. So it's a matter of keep observing. On the other hand, we have the supernova remnant scenario, in which you have something like the FRB source, which could be the magnetar, and somehow this source is emitting the flares that shock this expanding supernova remnant, and the burst is generated. Most of the mechanism to explain this will be something like a Maser mechanism. However, in the expanding supernova remnant, what we would expect is the DM and the maximum absolute value of the rotation measure to change in time, because this supernova remnant is expanding, right? So those are the two scenarios that are, as of now, quite popular, but how can we know which of these is the key one? Well, this is hard to know, but there are some key open questions that could give some lights of which of them is the preferred one. There are some open questions in particular that these are interesting to me, because this is my main field of work, and is to try to understand what is the connection between being an active repeater, having a persistent radio source, and your host galaxy having high star formation rate. Is there something that we are not seeing? In particular, if we do a multi-wavelength monitoring, can we understand whether this persistent radio source is a AGN or not? In principle, this is possible. Also, if I want to test the magnetar in the vicinity of a massive black hole, can I see, I could use, for instance, the magnetars in the galactic center to see if somehow it can resemble some of the FRB characteristics. Some of you might be aware that in April 2020, something like that happened, which was a galactic magnetar that entered an active phase, and in which a radio burst was detected and was followed by an X-ray burst. So this is usually referred as an FRB-like event. And I mean like, because if you, in terms of energy, still several orders of magnitudes less energetic than the least energetic FRB that we know. So still we come down to the problem of how could magnetars could generate these high energies that we see in FRBs, because as of now they cannot. And also, what is the extent of the emission of FRBs? As of now, we are restricted in the radio range, so up to 8 gigahertz and down to hundreds of megahertz. Can we observe them in optical if I were to detect a simultaneous monitoring? Well, for this, more observations are needed. But if we, okay, let's say we discover what's the progenitor of FRBs. Doesn't mean that's it. We can take our stuff and retire. Not really, because then the next step will be to use FRBs as tools for cosmology, which has been proposed. The reason for doing so is because fast radio burst coherent pulse proves the intervening material between the point where it was originated and our own galaxy. So this is the same idea that, for instance, with pulsars, I can prove the interstellar medium. With FRBs, because they are located further away, I could prove as well the intergalactic medium. For instance, it's been proposed that I could use that FRBs could be used for testing the isotropy of the universe. And this is done by studying the dispersion measure fluctuations at different lines of sight. It has also been proposed that FRBs could be used to prove the reionization epoch. And for this, what I will need is the differential DA measures of FRBs, but at high redshifts. Nevertheless, what we need for these two and many other more is to find many more FRBs, but not just find many more of them, also associate them to their host galaxy, because we need to know what's the distance to them to model the material that is between them and us. Furthermore, FRBs have also been proposed to be useful tools for testing fundamental physics, in particular the rest mass of the photon. But for this, what we need to know is to model properly again the material between the source and us, because otherwise this delay that could be produced in frequency if the FRB were to have, if the photons were to have a rest mass, will be indistinguishable from the dispersion measure delay. So yeah, we need thousands of FRBs for these applications, and we also need to localize them. But this is when new facilities, innovative facilities, have a huge role to play in this FRB field. In particular, the ARGOS project that I was told today by John that I'm the first one giving the talk. So I don't know how aware you are of this project, but this is a proof of concept project to install a radio facility in Crete, and the coordinator is John, and there is a series of institutions that are connected with this, among them the Max Planck Society, from which I am part of. So what can we expect from ARGOS? Well, the concept of ARGOS is a leading edge, low cost, and sustainable radio facility in Crete to be integrated into other world facilities, for instance, to do pulsar timing arrays. There are several key questions that ARGOS would like to answer, but in particular, I will focus on fast radio bursts to continue with the topic of this talk. And I will briefly discuss what's the main goal of ARGOS. So afterwards, we can move to the earliest stage, what we could expect. So in its full mode, ARGOS would expect to have around over 1,000 dishes, each of them roughly 6 meters. And because of this, it can achieve a sensitivity of a CEFD lower than 9 Jansky, which could allow to detect thousands of FRBs per year. You may recall that early during the talk, I said that the benefit of CHIME is that it has a large field of view, but a fair sensitivity. On the other hand, what ARGOS is aiming is to have a large field of view, so roughly 5 square degrees, but also to have high sensitivity. And by arranging these 1,124 antennas in a compact array, but also to distribute some of them scattered away, then you could do as well imaging. But if we come to the early stage, so how to start this? So if we take a smaller array of telescopes and you build the idea of a modular design, so it means that I start, I don't know, with 12, with 20, and then as everything starts working, I start incorporating more and more telescopes, right? Because the main idea first of this ARGOS project is to validate the array setup. For instance, okay, in principle, up to 6 meters, you can find industrial telescopes, so you can purchase them to see how everything will work. Afterwards, you could make in-house instrument or by the different partners in this collaboration. But we need to work on the data flow. How does the data record? And we need to combine the data from all the different telescopes, so there is a correlation there. And the larger the number of telescopes we include, then the larger the computing. Also, because of the sensitivity that ARGOS is expected to have, we need to also see how do we process this data. We will be collecting terabytes of data. How do I process this in real time and also send the triggers so other facilities around the world can also go and observe this? And as I mentioned earlier, for instance, for fast radio bursts, they can be as narrow as microsecond, which means that I also need to have the resolution to be able to see bursts with such a short duration. So all this is non-trivial. And the other thing to come for sure is the position calibration, polarization calibration that you need to sort out before you start adding more telescopes. The ultimate goal of ARGOS as well will be to be sustainable. For instance, can this be solar powered? You will need the panels, you will need the batteries. How much do we need for an array like that? By having a small scale, you could sort out all these complexities so you can bring the full array to maturity with the full ARGOS and 1,000+ dishes. But let's start small first, and this is some brief calculations that I was doing here. So in a pathfinder mode, so to start exploring how good the RFI conditions are, how sensitive we are, let's imagine we start with 12 dishes of 6 meters. We just put them in a compact grid, which means the only thing that I need to take care of is that the beam of each of them does not overlap, so they don't shadow each other. I don't need to cool the system, although from 1 to 3 gigahertz, it's non-trivial what the system temperature will be, but let's imagine that we use something like the technology that Chime uses for their LNA, which actually provides system temperatures of roughly 50 Kelvin, which is extremely good for an uncooled receiver. And then the other thing will be dual polarization. So with this setup of 12 dishes of 6 meters each, then I would expect to have an area of 204 square meters, which means, in simple words, that it will be equivalent to a 21-meter dish, which in fact is not small at all. With this, the sensitivity in terms of CEFD, or system equivalent flux density, will be roughly 900 Jansky, which is translated into minimum detectable fluence of 4.4 Jansky millisecond. To give you a number on how sensitive we could be, for instance, if we were to do a search, then we could already detect tens of new FRBs every year. Now, this number is always tricky to calculate because most of the studies that we have for the FRB population and spectral index comes from Chime, which works at way lower frequencies from 400 to 800 megahertz, right? Anyway, if I were to have this fluence, then it means that also some of the repeaters that we know as of now could be visible. For instance, FRB 121102 with luck, some of the bursts of FRB 190520, and also the Chime repeating FRB, which has, by the way, seen to frequencies as high as 6 gigahertz by our team here in Effelsberg. What I would like to emphasize is that already at the early stage, in the Pathfinder stage, science can be done. So as we sort out all the difficulties of having the arrays, also we can gather data that can allow us to do science. For instance, the monitoring of some of the FRBs to trying to find the activity windows. In this case, we could collaborate with some other radio facilities doing surveys. So when there is a repeater, we know, and then we start observing. We could also study the evolution of the dispersion measure and rotation measure to see, okay, which scenario maybe it's more favorable. Is it the magnetar embedded in a supernova remnant, or is it something like some binary? Also, if we find more FRBs, if we put some telescope a bit outside from this compact grid, we could also do imaging. Perhaps we could detect even the persistent radio source in some cases. The bonus will be that already with the sensitivity to be achieved by a 21-meter dish, already in 30 minutes to 1 hour observation, we could detect hundreds of the pulsars that we already know, which means already, provided that there is a maser clock, you could start doing timing and to be included in pulsar timing efforts, pulsar timing array efforts, for instance. So just to wrap everything up, FRB field or FRB science is changing quickly. It's fairly new, so we have been doing this for less than 15 years, but there are many science breakthroughs coming from this field. We have learned a lot of them regarding the repetition, their complex and dynamic environments, and how some of them are particularly interesting regarding their associations to host galaxy and persistent radio source. More interesting is that as we find more FRBs and as we localize them, then we can use them as tools for cosmology or fundamental physics. And this is the place where radio facilities, future radio facilities such as ARGOS, have huge potential to detect many more sources, but as well to localize them, which again will be key for the applications of FRBs as tool for cosmology. And having said all that, I would like to thank for your time, and I will be happy to take some of your questions. Thank you.
Thank you very much, Mary, for this very exciting talk. So clap for everyone. Are there questions for our speaker? We have about 5 minutes for questions. So I have many questions, so I can ask a few things.
Go ahead.
At some point, you mentioned that this, super fast radio bursts of microsecond duration. I know there's some publications coming up for that. I've heard about that before. I was wondering, is anyone actively searching for very slow, let's say, well, not super slow, but slow radio bursts? For instance, there was this famous wow signal in the 70s that was like 70 seconds long, and probably I know that most FRB pipelines would not be able to pick that up.
Yeah.
Do you know if I mean, just out of curiosity, is anyone searching for these things?
I would say in principle, yes, because if you already have the data, so a natural thing will be to go and reprocess the data in the broader range, which was already one of the points we brought up with the Effelsberg study. But while with most of the recording system we have as of now, we can go for narrow bursts in the microsecond range. The issue towards the longer range will be mostly radio frequency interference, I will say. So I will guess that this is one of the key factors preventing us from actually finding this second duration FRBs, because most of the radio frequency interference that we find is actually in this range. So we will end up having thousands to millions of candidates, and then how do you go through all of them? In principle, yes, we have machine learning algorithms for giving us a shorter list of candidates, but still it's quite challenging. So I would say it's possible, but extremely challenging in terms of computation and the number of candidates you will end up with.
Right, so you cannot utilize the dispersion measure to discriminate between RFI and fast.
Unless it's quite obvious, right? So in principle, yes, if you have a dispersion value of 0, yeah, okay, this is terrestrial. But then the problem is it's about the number of candidates. If you search all the way from 0 DM to 3,000, 4,000 in DM, then you will end up having a lot of candidates that afterwards you need to manually go. And furthermore, although we like to think that for radio frequency interference, the candidates will have DM0, there is always some alienation of parameters that will give a higher value. So I would say it's mostly computationally tricky. It's not impossible, and I will guess that many people are already reprocessing their data.
Understood. So thank you very much, Mary. Other questions for our speaker? Okay, if not, I think people already know how to contact you, Mary. So thanks again for this exciting talk, and thanks for introducing ARGOS to people, and hopefully we'll repeat this in person next time.
Yeah, definitely.
Yeah, okay. Bye, everyone. Bye, Mary.
Bye-bye.